Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear student, last time we were discussing about monitors, okay? And we couldn't finish that actually because of a few things back in home. So, when we talk about monitors, we saw that they are better than the semaphores because in semaphores we had the wait and signal that is to be done by the programmer, and they need to be in a particular order. So if you have to lock a critical section, you got to do wait on semaphore and you got to do signal on semaphore. And also if you have got to do signaling or synchronization between two processes, for example producer consumer, that's again being done by the counting semaphore or something else, but again using the wait in signal. So as a programmer, you may forget to put up a signal to the wait, or you may write in a different order the wait and signal, which can create a deadlock, okay? Or you may mess up with the signaling semaphore with the locking semaphore, and you can as a programmer do a lot of bad stuff to it. So it's gonna generate errors, it's gonna have deadlocks, and it can create a lot of problems to us. So we say that we need all these things done automatically. So what we do is we have a higher level abstraction. We have a class called monitor, and we give this job of putting variance signal. Say for example there's a wait and you have to put a signal. That means actually what you're gonna do is lock and then you release lock, and we say that this thing should be done automatically, so that when there is a lock, the compiler know that it has to do the release lock. As a programmer you can forget, but compiler will not forget because it's programmed to do so, and it will do it perfectly. So this code of locking and unlocking and all these things, this should be generated automatically. For example, we have today Java programming, and we have objects. We create objects in Java, and every object has its inbuilt lock. Okay, every object has a lock, and which runs a monitor program, and actually does all those things which monitor does. Okay, inside the monitor, it is done by the semaphores only. uh, the monitor inside is implemented like putting the these locks and waits and signals, but as a programmer you don't have to do anything. It is being done all automatically. That is the main point, so that you will not mess up with the waits and signals. Okay, and in Java we may have the synchronization keyword. We got to put up any method, put up in front the synchronization, that will actually make it apply the monitor code on that method. Okay, so monitor has what? So monitor is a kind of class where we have a shared data, and we have the procedures, say procedure 1, procedure 2, procedure 3, and we may have some initialization code. Okay, and the mutex is done by the monitor because only one process can access the procedure. And we told also in the last video, we discussed that if we have to do synchronization, then further we have conditional variables. Okay, that is also a difference between semaphore, because semaphore does conditional, semaphore does locking as well as synchronization, conditional synchronization by the semaphore itself. But here monitor is doing in a different way. If you have to do conditional synchronization, that is done by the conditional variables. Now here you can pause the video and have a quick read to this. So only monitor guarantees mutual exclusion because only one thread can execute any monitor procedure. So if this is a monitor and one guy is actually inside a monitor, and if other process comes in, so you need to have a queue of at the entrance where all those blocked guys are sleeping. Okay, and we may also have inside the monitor queues. Okay, if we have the conditional variables. For example, let's write a simple code. Say we have a monitor called say counter. Okay, and we got here int count, and we have a method here which returns the integer variable count, and we call it increment. Okay, and it has something like it is nothing, but inside what it does is it is only count plus plus. Okay, and it returns the count. Okay, that's it. The very simple monitor program we have. If you tell now two processes comes in simultaneously, maybe three processes or four processes come simultaneously to access this shared variable count. Now this is our critical section kind of thing. Okay, and we want that only one process should access it. So now say for example what we are doing is definitely we're going to create the object of this counter, of this monitor, that's a counter, and then we invoke the increment method. Now P1 is trying to invoke that increment method, and P2 and P3 P4 are all trying to invoke that you know increment method, right? But the thing is that as a programmer, you don't have to write a single line of code like that. You have to only specify that this counter is inside a monitor, okay, and rest lies with the compiler, because compiler will not allow uh, these all these processes to access simultaneously this method. Rather, it will be done one by one. Okay, so it will be the compiler who maybe he will compiler will allow P1 to go for increment, okay, and the rest of these guys will be in a queue. Okay, does make sense? But now there may be the situations that if for example P1 is going inside the critical sections, it's executing the monitor code, this increment method, and inside the monitor, for example, this process or this thread wants to sleep. It wants to wait on a particular condition. Okay, for example, we have producer consumer problems, right? And the producer has produced one thing, okay, one item, and consumer enters the monitor, because this is a shared buffer. This is the buffer and this is the procedure, and consumer enters the procedure and actually consumes one item from the buffer, and there is nothing now. Because there is nothing on the buffer now, even though it is inside the monitor, it has to sleep within the monitor, right? So these things can be done by the conditional variables, where we can do the synchronization stuff, where you can sleep or wait inside the monitor. For locking, you got to do nothing at all, because it is done all automatically. Let's take up a full example of bounded buffer problem we discussed earlier in the using the semaphores. Now let's rediscuss it using the monitors. So this is a typical example of monitor where we have a shared buffer. This is our shared buffer, okay, and we have the conditional variables. For these will be used for signaling, and there are some other integer, some other variables. They are all local to the monitor. Even the conditional variables are local to the monitor, and there are some procedures. We got a couple of procedures here. Excuse me. So this is the one procedure, and this is the another procedure, right? One is the append is the one procedure, and take is the item take is another procedure, because we know it's a consumer producer problem. And there is some initialization code as well, which initializes few variables. Okay, so we have here next in and next out. Next in will tell us where we're gonna put append in a buffer, and for example this is a buffer, okay, and where we are going to put, this is the next in. Say for example this guy will tell us where we're gonna put in, and next out will tell us which item we're gonna take, and count will tell us how many slots are actually filled. If count will be 0, that means buffer is empty. And if count is equal to k, because we are telling that we have a k size, that means this buffer is full. So uh, uh, um, more specifically, that if count is k, we can't append it, so that's the problem with the producer. And if because this is a bounded buffer, and if count is 0, that's a problem with the consumer, because we can't actually take any, because it's empty buffer, so we can't consume. So we should actually sleep inside the monitor. Okay, you should remember that on conditional variables we gotta sleep inside the monitor and try and see um, actually sleep on a particular conditional variable. And when when we got the signal for that that condition variable, then we can wake up and do our job. So we have an append method here, procedure here inside the monitor. Okay, this is the procedure 1, this is the procedure 2, and at a time, if two processes comes in, where a producer and consumer both come simultaneously, it is the job of the compiler to only allow one, so we don't have to do anything for that. Okay, only thing is we gotta do for signaling. If we want to sleep inside the monitor, so what we do for that? So for example, producer process comes in, and say for example we have filled the buffer full. If we have filled the buffer full, then count will be k, right? So that's what we do here. If count is k, we actually sleep. What will wait only do the blocking. Okay, whatever it does, it will do it automatically, and it will block a process on not full. Okay, so this not full is the conditional variable not full. If not full will tell us about the space, and this not empty will tell us about the value in the buffer, right? Okay, so space is even when the space is not full, until then we're gonna wait. This is what we can put to this thing. So if count is not equal to k, that means count is lesser than k. Okay, and then we can only do one thing. We can append whatever the v is, whatever we want to append. And because anybody calling this monitor will call this method append and actually send a value to this v. Okay, that v is to be put into the buffer at nextin, where nextin will tell us where we want to put it. Okay, and nextin, when you put something, say for example here, now nextin is to be incremented in a cyclic manner. Mod k will get it back if it is the end. We know that, we have done it a lot of times now. And also we have filled something, so count will be count plus plus. So initially there was nothing, this thing will not run. Okay, because count is this time 0 in the beginning. So you append whatever you want to append at the first position. Okay, so that's why next in is at 0, next out is at 0, count is 0 initially. So at the 0th location, that is the 0 of an array of the buffer, you append that thing, and you also say count plus plus. That means now count is equal to 1. Okay, and when you're done that, you can maybe before this process, consumer process came in, and consumer process has called this method, that's the take. Okay, but in the beginning count was 0, so that would be stuck in this. If count is equal to 0, yeah, that is, so not empty dot wait. So it will actually that process will be sleeping on not empty. Okay, on the conditional variable not empty. Now if after that consumer process, the producer process produced this a, and count plus plus is 1, now you can actually signal your process which is sleeping. Okay, if it is sleeping. So in this case, if we say this, yeah, it has came before the producer process and it was sleeping because there was count 0. So it will not empty dot signal will do what? It will wake up one particular process which is waiting on not empty, the conditional variable. And yeah, we were sleeping on this conditional variable not empty consumer process, so that will wake up and start consuming that. At the next out will tell us where that a is, because next out is initially at 0. So you will tell us where that is, and you increment the next out to the next here, right? To the next place. And also you do the count minus minus because you have actually consumed this, so it's no more there. Okay, that's why you say not full dot signal. Not full dot signal. Why you do not full dot signal? In this case, there was nobody waiting, so not full dot signal will be lost. So it will be of no use, but it will not create any problems. It's not like unlike semaphores actually. Okay, because signal in semaphore always increment. Here it does nothing because nobody is waiting. But maybe we have a producer process come all the time, k times, and it has filled all this buffer. Now that means a producer process again wants to fill the buffer, but it is stuck here. If count is equals to k, it is equal to k this time. Okay, because we have full, so we are waiting on the not full conditional variable. So you are sleeping, this buffer is sleeping on the not full. Okay, on the conditional variable not full. So when you are sleeping on the not full, this process when comes in and consumes something, it consumes say for example a or something, it consumes it, and and also this in variable, this wherein, because you have reached here, after that it will do mod k, so in will be pointing to this. Okay, now say for example this was the first guy, out is also pointing, next out is pointing to this also, so you consumed that. Okay, and here you did count minus minus, so count becomes k minus 1. If k is say for example 1 2 3 4 5, k will become 4, and you also signal somebody who is waiting on the conditional variable not full. And yeah, we were waiting here for the not sorry, here not at the not full, we were waiting here. So this process, a producer process, will wake up and start appending at the next n, and so on. Okay, so this is how the bounded buffer work with the monitors. If you are not getting properly, you should also watch the bounded buffer problem using semaphores, the old video, and then come here and you will get it exactly. So we have a situation like this, that there are some processes which are trying to enter the critical monitor to access the critical section, that is the bounded buffer, and but only one process, say this process, enters, right? These guys stay in a queue. These are outside, but actually I should show it like this because they are inside the monitor. Okay, and now some processes maybe after processes enter and leave, there may be some process entering waiting for the condition not full. Okay, and some process may be waiting on a condition not empty. Okay, so then there may be some signaling being done. When you are signaling a particular process, you are actually waking some process up, is it, to enter the monitor, and so on. Now here we gotta think about this sleeping and the releasing of locks. Yeah, I'm saying that we have a monitor and there are some processes waiting to enter, and some process is, say there will be also some queues inside the monitor, say I make it here, which are waiting for some conditional variable. Say these guys, these are waiting for some conditional variable, and these are waiting for some other conditional variable, and so on. So one process is actually inside a critical section. Now we are saying that say for example this was the producer consumer process, and a buffer was full. Okay, now one consumer process comes in. This is a consumer process. It actually consumes this. So when it consumes this, it is an empty slot now. Okay, so that means a producer process, for example, it can now carry on. So it does signaling. Okay, like we did on the top, we said we did the signaling here, not full dot signal, because our consumer will be waiting, would have slept on the not full. Okay, so our producer will do not full dot signal. Okay, when we do not full dot signal, but before entering into the critical section, that means this process before entering into the monitor, actually this process will be given a lock. This will definitely have a lock. That will be an automatic lock given by the compiler. So this process will definitely have a lock. Okay, so lock is with this guy, right? Now if we are saying that if this does not full dot signal, that means it will wake up some process or thread from the conditional queue. Okay, conditional waiting queue, say this one. Now that means it can now enter into the monitor, right? So it can execute the monitor part of code, but that means it should also have a lock when it enters. So question is, if both of these guys will enter into the monitor, then the whole purpose of mutual exclusion is gone. Okay, that means we can have out of these two only one, either the guy who does the signals, so signaler, okay, can have a lock, or the guy which is being signaled can have a lock. Now who else will have a lock? Depending upon that, we actually, because only one can have a lock, right? So depending upon that, we have two kind of monitors. One is called the Hor type, and another one is called the Mesa. Okay, let's try and discuss now these two things. This thing is called as a signal semantics, and we have two flavors of monitors which differ in the scheduling of semantics of signal. Okay, the first original one, Hor's monitor 1974, okay, wherein we have a signaler which yields the monitor to the released thread. Okay, that's what we are saying is we have say for example some uh, process comes in, and it actually is waiting for, say for example, just on above we have a consumer process which was sleeping for the not full. Okay, producer process just sleeping for the not full. Now not full occurred, it came before, the producer process came before, but because of the buffer is full, it is waiting on the not full. Okay, now it is waiting in here in a sleep queue, and this is the suspended queue, and because it is suspended, it's a sleeping queue, it's not ready. Okay, and some other process comes in, maybe consumer process comes in. Okay, now this is say for that consumer process. Now it is executing, and after consuming, it finds that count has you know it decrements the count, and when it consumes, it actually does not full dot signal. This guy has done the not full dot wait, so it is in a suspended sleeping queue. And here the consumer process actually does the signals, so that means it wakes it up. So when it wakes up, who will get a lock is the problem. The whore says, according to the whore, what happens is it relinquishes the lock. The C will go itself to the suspend queue. Okay, that consumer process is C, go suspend queue, and this process comes in and starts executing its monitor program. Okay, so whatever it want to do. So signal immediately switches from the caller to the waiting thread. So this was the caller who actually does the signal, and the waiting thread gets the chance, and it's more like we can say it's doing more justice, because this process has come much earlier than this process, and so it should get the chance as quick as possible because it's waiting. Okay, and it has come earlier, so it should get the chance, and it is getting. Now this process is C. Say this was the D process which was waiting, and C process is the, or I should say P process, producer process, and C process is the caller which actually does the signal. Now C process is suspended, okay, and P process is loaded. Now P do not have to chuck the lock because it's given immediately, the lock. So one more advantage is it does not have to chuck for the lock, because when it came, when the P process came, it had a lock, but when it's suspended, it releases the lock, so it is in a suspended queue because it was waiting for not full. Now when a consumer process comes in, it has a lock. Okay, okay. Now when it signals, it actually have to release the lock and give lock back to the P. Now P does not have to check whether lock is with him or not, because it is guaranteed the lock is there. So that is a good thing we can say here, that it does not have to check for the lock again, so it can go ahead and go for monitor and don't worry about the lock because it's with you. Okay, now Now we have another version of this scheduling, semantics, what's called the Mesa. And Mesa basically is a programming language. You should know that Mesa is a programming language. It is developed by a group of Xerox research in late 1970s. So somewhere in 75, 78, something, which supported this programming language, by a group of Xerox researchers. It supported multi-threading. Okay, you should remember that it supported the multi-threaded programming. So Mesa also implements monitors, but it goes for a different style. Okay, in the horse type, the signaler uh, process actually yields to the waiting process, right? But here in the Mesa, the signaler process, okay, say for example here the consumer process, the signaler process, and producer process was the waiting process. The signaler process does not yield. Okay, it continues, it holds. So when it holds, what will happen? Okay, because it's not yielding, okay, it continues. So when signaler continues, actually, that means it's no more suspended. So it is a ready. Now P will switch to the ready queue. Now P is not in a sleeping or suspended queue, because it's no more waiting for any conditional variable. Okay, but rather it's ready to go, but it does not have a lock. Lock is continue with this process. Okay, consumer process. So consumer process may do all its stuff of monitor what it has to do, but in case consumer process has to yield immediately, so it has to suspend its job. It is to go in a suspended queue like the P, and then P continues and the P yields. It will actually then after then the consumer process will come up and finish its monitor job. But here in the Mesa, the consume this signaler, which is doing the signaling, here in our case the consumer process, actually continues. It does the signal when it says notify.signal. It says notify.signal. What it does is, it by that producer process which is waiting on the notify.signal actually wakes up, but it's not given the monitor. Rather it goes into the ready queue. Okay, it has no issues, it can go for, but it's waiting. Because why? Because it does not have a lock. Only one process can be in a monitor. Now when consumer process finishes, but at that moment the P is not sure that it has lock or not. Why? Because if it finishes, okay, now because it has done its waking up job. Okay, that is being done by the C. Now when it finishes, it releases a lock and goes away. Okay, when it goes away, there is a chance that some other process comes in from the entrance queue, okay, and locks the monitor and enters. So P may not have a lock. Okay, so in this case, before P can go for a monitor again, it has to again seek for the lock. It has to see whether the lock is with it or not. In this case, there was no problem of locking, because when a consumer process actually does a signaling, it simultaneously yields the lock, and that is the lock will be with the waiting process. But here waiting process is not necessary that it has a lock. Okay, so that's what we say here. This is done in a Java or a Mesa. Places a waiter on the ready queue, but signaler continues. Signaler gonna continue. That's in our case the consumer process. Okay, condition is not necessarily true when waiter runs again. So it's not necessarily true, because some process may have come up and taken the lock. Okay, um, so that's why you gotta recheck the conditional case. Okay, what can happen here is maybe some process, because you are waiting for not full and consumer process is taken up, maybe some other producer process come up and fill the buffer. So now if you come up, you think, oh, uh, there is some space left, but maybe the other producer process have come in the meantime and fill the buffer again. So for you, still buffer is full, so you have to recheck that conditional case. So if we see here, uh, this is this Mesa or the whore? Okay, this is definitely the horror, because when you are sleeping on a certain condition, okay, you chuck the condition, okay, you are sleeping, so when somebody is waking up, you are not chucking, you are going directly doing your rest of the monitor stuff, okay, this thing. So I'm saying, say for example buffer is full, okay, you chuck the condition, our buffer is full, yeah, it is, count is k, equals to k, that means buffer is full. So you say not full dot wait, so that you will sleep on the conditional variable not full. And after somebody wakes you up, so producer process comes in and actually consumes and does not full dot signal, so that can wake you up and you can straightway do rest of this code, okay. But this will not work with in the case of the Mesa style of this scheduling. Why? Because when you do not full the signal, you are not gonna actually release the lock. You are gonna do the rest of the things unless you're finished. In the meantime, some other process may come up, and when you are done, you will release the lock, and some other process may come up, and you're not guaranteed the count is now not equal to k. So you have to recheck this condition again. So you can't use the if here, rather you have to use this thing in a while loop, okay. You got to do this in a while count equal to k. So you can't use an if, you have to use the while now for the Mesa, so that when you come back, you are actually in this loop, okay. So you say while again, so you are not actually if chucks only condition for once, okay, but while will recheck it, so you have to recheck the conditional. So that's why we are saying that in a whore you can say a condition if empty, then you do wait condition, okay. If there is some slot left, if as we say that count was not equal to k, or if a k count is equal to k, then you don't wait. But in the Mesa you got to do the while. Why? Because you have to recheck, you are not sure the lock is with you or not, okay. Now there's some trade-offs. The Mesa ones monitor are easy to use, they are more efficient because some while loops to recheck it, no problem. There are fewer context switches, easy to support broadcasts, and Horse monitor leaves less to chance, easier to reason about the program. And why we say that, because say for example you have a time slice given to a particular process, and in the meantime if some other process comes in, but if you don't release the lock, okay, if you give immediately lock to the other guy, it may waste some CPU time. So we say that this one is more easier to use and more efficient, because it will not actually lose even a bit of a time, because the moment it releases a lock, it completes the firstly the consumer process, because maybe it has some time slices still left, otherwise you have to do more context switching, okay. Are you getting my point? That's what I'm saying, is if there is a consumer process going on and it has done some monitor, and this much is left, okay, this much monitor is done, this much is left. Now because at this point you do the signaling, at this point you are doing the signaling, now you have to release the lock as per the whore, okay, you have to release the lock. Now that means when you release the lock, you have to context switch, because this much is left out, and later on you have to come back again for this much only, okay. But in the whore, what you do in the Mesa, what you do is you don't release the lock, actually you finish completely this thing, so there is no context switch here. And uh, and also maybe the time slice is with some other process which was waiting, sorry, no, not like that, because they will not be given any time slice because they are waiting in a sleep. Actually this will have a benefit that we don't have to context switch on this process, okay. So this will be done completely, and after that some process may come up, okay. Even some process which is just come in, can come up, okay. That's why we say it's easier to reason about the program, because as a programmer we say that the waiting process should get a more chance. So that way the horse monitor will be better, because it gives the waiting process more chance. But in the Mesa there is no less context switch, but the process which has just come in can execute the monitor and the waiting process can still wait. So that is the trade-offs between the two. So hopefully I think we are getting this monitor stuff. Okay, so we can go for more example like a classical problems we did with the semaphore. We can do them with the monitor as well. So they will be now our next stuff. Okay, so till then, masalama.